Alright, today I want to go over section 10.6, which is looking at conic sections in a different way in polar coordinates. In section 10.5, we went over polar coordinates in rectangular or conic sections in rectangular systems of coordinates. Here we're going to do polar coordinates. We will define them all in terms of the same approach. Like in 10.5 we defined the parabola in terms of focus and the directrix, whereas we defined the ellipse and the hyperbola in terms of the two foci or two foci. In this section we will do a unified approach to all three conic sections, and here it is. So let F be a fixed point. That fixed point, as we all know it, it's called the focus. And L, let L be a fixed line. That fixed line is the directrix. In a plane. Let E, as we know it as eccentricity, be a fixed positive number. Which again, it's the eccentricity. The set of all points in the plane, the set of all points P in the plane, such that the ratio of PF to PL, and since this could be negative, so we'll just put absolute value equals E. So you can see we define the ratio of the distance from the point to the focus to the distance from the point to the directrix is a constant, and that constant is the eccentricity. Is a conic. It could be one of these three conics such that it's an ellipse if E is less than 1. Again, just so you understand, in an ellipse, E equals C over A. In an ellipse, this is A and this is C, focus, vertex. So obviously C is less than A, or C over A is less than 1. So if C is less than A or E is less than 1, then we get what we call an ellipse. A parabola, if E equals 1, again, this is C over A, and in a hyperbola, over here, the best way to look at it is when we defined focus parabola PF. Remember we said in a parabola PF has to equal, if this is PA. Okay, so if these two are the same, then we get a parabola. So PF over PA is, which is E in this case. And it would be a hyperbola if obviously E is greater than 1, which means C is greater than A. And in a hyperbola, this is the focus, C, this is A, vertex. Okay, so if E is less than 1, we get an ellipse. If E is 1, we get a parabola. And if E is greater than 1, we get a hyperbola. E is the ratio of the distance from a point on the conic section to the focus, to the ratio from that point to the directrix. Keep that in mind. So now we're going to talk about polar equations of conics. So how do we write equation of a parabola, hyperbola, and so on in terms of r and theta? A polar equation of the form r equals ed over 1 plus or minus e cosine theta, or r equals ed over 1 plus or minus e sine theta, represent a conic section with eccentricity E, and most importantly, focus is at the pole. So that's, you know, if the focus is anywhere in the plane, you just do a translation and put it at the pole, which is the origin in terms of rectangle. Okay, so if the focus is at the pole, the conic is an ellipse, as we know, is an ellipse. If E is less than 1, it's a parabola. Just like before, E is 1. Hyperbola if E is greater than 1. And what is D? Well, the absolute value of D is the distance between the focus and the pole. Distance between focus, which is at the pole or the origin, and the directrix, as always, directrix. Okay, so basically, just to give you an example, you could have focus here, which is the, so this is the rectangular system of coordinates, the y, the x-axis. This is x equal negative d. This is the origin, which is the pole, and d, this is the absolute value of d. Okay, or you could have a focus at the pole and y equals d. So this is d. And you could have, you know, all the other cases. I'm just showing you 2 cases. Alright, so which equation? See, there are 4 equations here, right? So which one represents which conic? So here's the 4 types of equations. The 4 types of equations can be classified as follows. In this case, we're going to assume this positive. If it's negative, we do absolute value. So we have a horizontal directrix above the pole, which is the origin. R equals ED over 1 plus E sine theta. So if we have horizontal directrix above the pole, okay, horizontal directrix above the pole. If we have horizontal directrix below the pole, then you use this equation, ED over 1 minus E sine theta. So basically, this is the focus, which is the pole, and this is the directrix. Okay, so use that formula, and it doesn't have to be a parabola. I'm showing you a parabola. It could be anything. It's based on E. Okay, you have a vertical directrix to the right of the pole. R equals ED over 1 plus E equals sine theta. So this is the focus, which is the pole, and we have a directrix to the right of the pole. So basically you will have directrix. And if you have a vertical directrix to the left of the pole, then R equals ED over 1 minus E equals sine theta. Okay, and all these are in the book. So here's an example, number 2, page 17. Let's look at page 717 in the text. Number 2. It says write a polar equation of a conic with the focus at the origin given data. So we know it's an ellipse, and we know from the value of E, even if they didn't tell us E is less than 1/3, and Directrix y equals 6. We don't have to graph it, but so we want to get an idea. So the focus is right here. Directrix is y equals 6. So it would be r equals, so we have a horizontal, which is above, horizontal directrix, which is above the focus, so it's r equals ed over 1 plus e sine theta, right? Horizontal directrix above the focus. D is positive, it's that distance, which is 6 units. E is 1/3, 1/3 sine theta. So r equals 2 over 1 plus 1/3 sine theta. If you want to get rid of the fraction, you times by 3, top and bottom. You get 6 over 3 plus sine theta. Number 8. So you have a hyperbola. Obviously in a hyperbola, E has to be greater than 1. It's 2. And directrix, r equals -2 secant theta. Well, we're used to directrix being x equal or y equal. Don't forget that secant is 1 over cosine. So r cosine theta equals -2. So x equals, so they're trying to trick us, okay? So x equals -2, and E is 2. So the focus is right here. Directrix is x equal -2. So the directrix is to the left of the focus, so it's r equals ed over 1 minus e cosine theta. E being 2, d being 2, it's positive, it's absolute value. It's 2 cosine theta, 4 over 1 minus 2 cosine theta. Alright, number 12. In number 12, it wants us to match the equation with the graphs 1 through 6. Give reasons for your answer. 12. R equals 12 over 4 plus 3 sine theta. So we want to have to look like the 4 graphs that we talked about, the 4 equations. You're going to have a 1 here, okay? You're going to have a 1, so you're going to divide everything by 4. So you get 3 over 1 plus 3 over 4 sine theta. So we have a conic with directrix above the focus, and E is 3 over 4 less than 1. That means it's an ellipse. And if you look at the graphs, there's 2 ellipses, number 2 and number 5. It's number 5. It's number 5 because if theta equals 0, then we can put any theta, but the easiest theta equals 0, then r would be 3 over 1 plus 3/4 sine 0, which is 3. So r would be 3, which is more reasonable than number 2. So it would be number 5. If you still don't see it, do like theta equals pi over 2. R would be 3 over 1 plus 3/4, which is 3 over, that's 7 over 4, 12 over 7. Okay, if you try theta equals pi, that's 3, which looks more reasonable. Okay. Alright, so number 14. Number 14, you can do that, okay? It's just the same kind of question. It matches graph number 1. Let me just find the reason for that. No, the answer is in notes. Number 20 now is the same. In number 20, find the eccentricity, identify the conic, give an equation of the directrix, and sketch the conic. Okay. So R equals 1 over 3 minus 3 sine theta. So we want to have a 1 there, so 1/3 over 1 minus sine theta. So since E is 1, right, we have a parabola with directrix below focus from the equation, okay? Directrix is below the focus. Now this is ED. ED is 1/3 and E is 1. That means D is 1/3. And the directrix, it's gonna be Y equals negative 1/3, because let me explain that. So you have the focus is at the pole, always in this case, X, Y. The when theta equals 0, when theta equals 0, you get 1/3. So this is theta equals 0. R is 1/3. So say this is 1/3, 0. And when theta is pi, it's also 1/3. R theta. And the vertex, now the directrix is, remember the directrix is below the focus. This is the focus. It's going to be d units, so it's 1/3. So the directrix is y equals negative 1/3. The vertex is halfway between the focus and the directrix, so it's the midpoint. So it's going to be at 1/6 and then 3 pi over 2, right? 3 pi over 2, 1/6. And that's the now one of the most interesting results about conics is Kepler's laws. And I'm reading the law in 1609, the German mathematician and astronomer Johann Kepler, on the basis of huge amount of astronomical data, published the following 3 laws of planetary motion. A planet revolves around the sun in an elliptical orbit with the sun at one focus, and it doesn't really apply only to the motion around the sun, it applies to the motion of the moon, the comets, and satellites. So a planet revolves around the sun in an elliptical orbit. It could be the moon, it could be the comets, they all revolve around the sun in an elliptical motion. The line joining the sun to the planet sweeps out equal areas in equal times, and the square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit. Of course, we're not going to see the full benefit of this, but we're going to get the equation. As a result of Kepler's law, the equation of an ellipse in polar, so equation of an ellipse in polar can be written as, so the equation that you have, we can write it in this way. R equals A into 1 minus E squared over 1 plus E. Because we can prove that, that's, to go from the other equation to this one. Again, focus is at the origin, where A is 1/2 major axis. So in the previous example, we didn't have A, right? We have R equals dE over 1 plus E sine or cosine, okay? There's no A. A, remember the major axis is 2A, so A is half the major axis. Okay, an important remark. So if you have, we're talking about elliptical shape, and we have the sun, and everything revolves around the sun, planet, moon, whatever, in an elliptical shape. So the sun is the focus, and you have angle theta. So there are 2 points, perihelion and aphelion. Perihelion is the closest to the sun. It's the closest to the sun, and the furthest. This is the closest. This is the farthest. I mean, the sun should be right here. I made a mistake. Okay. So the perihelion distance from a planet, perihelion distance, which is the shortest from planet, is A into 1 minus E, and the aphelion is A into 1 plus E. Here theta is 0, here theta is pi. If you put theta equals 0 there, you get cosine 0, which is 1. This cancels with that because this is 1 minus E, 1 plus E, and it gives you these results. Okay, there's an interesting example, number 34, page 718. It says comet Hale-Bopp, discovered in 1995, has an elliptical orbit with eccentricity 0.9951. So it's a comet, it's not just a planet. The length of the orbit's major axis, so the major axis is 356.5 astronomical units. So that's 2a. That means a is half of that, which is 178.25 astronomical units. Find a polar equation of the orbit. So remember the polar equation. Since we're given a, we can use this equation. We cannot use the other one. So r equals, a is 356.5. 1 minus 0.9951 square, 1 plus 0.9951 cosine theta. So if you do the math, it would be 1.7426, 1 plus 0.9951 cosine theta. How close to the sun does it come? So the closest to the sun is what? The perihelion, which is A times 1 minus E. So closest to sun is A into 1 minus E, which is the perihelion, 178.259951, which is roughly 0.8734 astronomical unit. What is this in miles? We know that an astronomical unit is 92 million miles, almost 93, 807.27 miles. So if you take this and times it by 92,955,807.27, you get roughly 81 million miles. See you there. All right, so that's it.